All right, we're going to start talking about atmospheric pressure in a moment. Before that, I want to remind you that based on the previous video, I'd like you to look at example 15.4 in the textbook and see if you can work it out on your own. This is a very simple example, and believe me, the textbook is meant to be used, so please get in that habit right away. All right, so let's get to atmospheric pressure. The atmosphere is made of a mixture of gases, mostly nitrogen and oxygen, and it's a fluid. The wind blows, fluids in flow, the air stays still, fluids static. So much of what we're doing in this chapter will be contrasting fluids as liquids and fluids as gases. However, the atmosphere is, of course, extremely important to us, to our survival, and it's also very interesting. Atmosphere is what gives us weather and climate to a large extent, for instance. So let's look at atmospheric pressure in more detail. Now, one of the things we talked about, and I'm reminding you quickly about this, is that the origin of pressure in gases is thermal energy, not gravity. So if you have a container that's, say, the size of a box, or this room for that matter, then the gas pressure at the bottom or the top is about the same as anywhere else in the room. And that's completely different from liquid pressure, where we just learned that liquid pressure increases with depth. Now, gas pressure is also susceptible to gravity, but only under circumstances where the box in which you have enclosed the gas is, say, 1 mile high or 2 miles or 5 miles high. All right, so to remind you, if this is the Earth, the atmosphere is this thin veil of gases, mixture of gases, that gradually fades out into space, into the void, the emptiness of space. And it is densest, closest to the Earth's surface, and that's because of gravity. So we see the effect of gravity on gases only when you have enough gas molecules in your container such that there's enough of a weight on it. So if your container is that big, say 1 mile high, then yes, indeed, the gas pressure at the bottom is going to be different from the gas pressure at the top. However, if your container is the size of a building, then the pressure at the top is really not that much different from the pressure at the bottom. So that's an important distinction to keep in mind. Gas pressure has its origin in the thermal energy of the molecules, but gravity does affect it only at large scales, which is why, for instance, the air in Denver is thinner than the air in Boston. So how do we measure atmospheric pressure? Well, we measure it by using liquids. And there are two instruments we're going to look at, the manometer and the barometer. And we are also going to look at a number of everyday phenomena that we are used to that has to do with the atmosphere and the atmospheric pressure. But let's get to the instruments first. So let's talk about the manometer. The manometer is simply a U-tube that's filled with some liquid. So it looks like this. And typically the liquid is some kind of oil. So you have this U-tube filled with a liquid, and you have the atmosphere pressing down on both sides equally, and also pressure depending on depth in the liquid, and therefore the levels are equal. Then, if you attach this to a container containing the gas whose pressure you want to measure, then we'll see something different happens. And there are two situations we're going to consider for the manometer. One is when the pressure of the gas is greater than the atmospheric pressure. So here's your container of gas, and you want to measure the pressure of that. And you attach it to the U-tube. So here's your manometer. Originally the levels were equal, but consider this. If the atmospheric pressure is less than the pressure of gas in this container, then what's going to happen? Well, as you might imagine, it's going to push down the liquid on this side, and so the liquid's going to go up an equal amount on the other side. All right. So how do we use this to figure out the pressure of the gas in this container? The way we do this is to recognize that since liquid pressure depends only on depth, the pressure within a connected liquid, in a container like that one, is going to be the same along any horizontal line that is within the liquid. So it makes sense to then look at 2 points within the liquid, point A and point B, which are on the same horizontal line and within the same liquid, although point A is just barely below the surface of the liquid here. We deliberately chose that for a reason that will become obvious in a moment. And then we can say with confidence, based on what we did last time, that the pressure at A must be equal to the pressure at B. Now, what's the pressure at A due to? This is where your physical reasoning comes in. So you have to think physically when you solve problems. Well, the pressure at A, if I imagine I put my hand here, there's not much of the liquid above my hand because A is right below the surface of the liquid. What's really causing the pressure here is the gas. So the pressure at A is nothing but the pressure of the gas. What about the pressure at B? Well, the pressure at B is due to 2 things, as you can see. Let's say that this height or the depth at this point is D. And so you have this much liquid. If you put your hand here, you'd feel the pressure due to this much liquid pushing on your hand, as well as the atmosphere, since this is open to the atmosphere. So therefore, the pressure at B is going to be density of liquid times G times D, the formula we derived earlier, plus the pressure of the atmosphere. And therefore, all you have to do is, if you know this depth, and typically manometers come with a scale, so you can read off that height there. If you know that, and you know the density of this liquid, typically some kind of oil, and you know the pressure of the atmosphere, then you can figure out the pressure of the gas. And at this point, it's let me add a note here, that the pressure of the atmosphere is, this is the average pressure at sea level. Now, atmospheric pressure, as we will learn, changes all the time, which is why we want to measure it, and the instrument we use to measure it, we're going to study in a moment, that's called the barometer. But just for a kind of average value at sea level, this is what the value is. So knowing that, you can figure out the pressure of the gas in this container. Now, that's the first instance, the first example, when the pressure of the gas is greater than the pressure of the atmosphere. And we see that mathematically that makes sense because you take P atmosphere and then you're adding a term to it. So this is going to turn out to be greater than P atmosphere. So let's go and talk about the next example, which is what happens when the pressure of the gas in the container is less than the pressure of the atmosphere. What will happen to the liquid in the U-tube? So here's our gas, and this time the pressure is less than that of the atmosphere. And so think about it for a moment. I'll give you a couple of seconds to think about what will happen to the level of the liquid. All right, hopefully the answer you got was this, that the liquid in this arm is going to be pulled up compared to the liquid on the other side, because the atmospheric pressure is less in the pressure of the gas is less than the pressure of the atmosphere. So if we do this, then we're going to have this situation for the case that P gas is less than P atmosphere. Okay, now how do we use this to measure the pressure of the gas in the chamber? Well, it's again the same logic as you can imagine. We use the fact that liquid pressure depends only on depth. We draw a horizontal line. The important thing about that horizontal line is that it must pass through the liquid and the same liquid. There are going to be examples we do where we have more than one liquid, but the only way that it works is if the horizontal line passes through the same liquid, and that's the case here. So again, we can assert that the pressure at A is equal to the pressure at B. And then we use our physical intuition to figure out where that pressure is coming from. So if you put your hand in A, you'd feel the push of this much amount of water or oil or whatever the liquid is, and that's D or H, whatever you want to call it. And you'd also feel the pressure of the gas. So our equation then becomes the following. what we feel at point A is P gas plus rho liquid G D. And if you look at point B, there's nothing really pressing down there other than the atmosphere. So we want the pressure of the gas, so we solve for this by putting the terms on the other side. And that's how we get the pressure of the gas in the container for the case that the pressure of the gas is less than the pressure of the atmosphere. And you can see it makes sense here because we're subtracting from P atmosphere in order to get this gas pressure. So the way to solve this, the manometer problems, is the following. You're going to see the general formula for liquid pressure, the one we derived in the last video, on a formula sheet. All right, and it's also at the back of the book. But if you use that formula blindly without looking at the context of the problem, then you're going to make a mistake, especially if you use it blindly here, because in that formula there's a plus sign, not a minus sign. But the minus sign is what makes sense here. And how did we get that? By starting from first principles, by starting from this process of recognizing that liquid pressure here and here are the same. So that's what you have to do for every problem. So this tells us how manometers work. There's a section in the book that talks about manometers that are used to measure blood pressure. And that is something I would like you to read independently so that we can discuss it in class. We are going to go on to talking about the pressure of the atmosphere itself and how we can use an instrument called the barometer to measure that pressure, and then we'll stop. So the barometer is an instrument that measures atmospheric pressure using liquid mercury. As you know, mercury is the only metal that is liquid at room temperature. This is how you make a mercury barometer. You take a container. So we're making a barometer. We take a container, fill it with mercury, and then you put a long tube inside this until the tube is completely filled with mercury. And then you raise the tube to a vertical position, being careful not to let any air in. And when you do that, then the tube becomes, some of the mercury falls down, and some of it slides down, but not entirely. And what you have up here is a vacuum, and it slides down and it stays at a particular height that we're going to call H, and that height is above the surface of the mercury. And the first thing we have to understand is that why does the mercury slip down? Well, that's because of gravity. It's heavy and leaves a vacuum above at the top of the tube. And the second thing to understand is that why does it stay static at a particular height? And for that, you have to recognize that the atmosphere is exerting pressure on the surface of the mercury. And if you think of the atmosphere as two giant fists, invisible fists, that are pushing down in all directions, including down, then you can see that the atmosphere pushing down here is what's keeping the mercury up in the tube. So depending on how hard the atmosphere is pushing, the level of mercury in this tube is going to change. It's going to slide up or down. So if the atmosphere is not pushing very hard, then it cannot maintain a very long column of mercury. If it's pushing harder, then the mercury will go higher in the tube. So that's the first thing to understand before we get to the mathematics, that it's a question of your physical intuition, which we're trying to develop here. All right. So now that we've got that, hopefully, we're going to make that more concrete by looking at the mathematics of the situation. So again, we use what we've done before. Our guide is that liquid pressure depends on depth. So if we mark 2 points, A and B, this is B here, this is A is just below the surface of the mercury, B is on the same horizontal line, then we know that since liquid pressure only depends on depth, we can make this statement that the pressure at A is equal to the pressure at B. And if we do that, then notice that the pressure at A is really only due to the atmosphere. So this is P atmospheric equals, and the pressure at B is due to the height of the liquid above this point, and there's no air there, so there's no contribution from the atmosphere or any other thing. So this is going to be the height of the density of mercury times the, I'm sorry, I called it H. So this is H times G. And so you can see that if you solve for the height of the mercury, I'm sorry, let's do it this way. A couple of things to note here. First thing to note, this tells you the atmospheric pressure is directly related to the height of the mercury column, so it bears out our physical intuition, what we earlier described, okay? The other thing it tells you is this, and this is really interesting historically as well. Back in the 1800s, when people first started to pipe water into their houses in Europe, so that they had running water for the first time in the house, they noticed something rather peculiar. They noticed that, let's say you have a pond here, and you're trying to use it to pipe water to a house. Of course, only the rich could do that at that time. So what they would do is they would take a pipe and they would use it as a siphon. They would take all the air out of it, fill it completely with water, put it in here, and the water would rise and turn on a tap, and there's your water. Well, it turned out that they noticed something, that if the height of the pipe or the height of the floor where they wanted the water to go, if that height was above a certain amount, no matter what you did, the water would not naturally rise up to that height. You needed a pump or something. All right. So in fact, that height was about 10 meters. And this was a real puzzle for people at that time until the scientist Pascal, who did all the studies about fluids that we rely on today, he laid the foundations of the science until he figured out why that's the case. And that's related to a question about the barometer. And my question is this, and I want you to think about it and come up with the answer next time we meet, which is this. Why is it that we don't have water barometers? Mercury is toxic, mercury is expensive, so why not replace it with water? And so I want you to think about it both in terms of the physical intuition about how the barometer works, and in terms of the mathematics. And if you look at the mathematics, you'll notice that we can actually figure out, as I was about to do earlier, but then I don't want to give away the answer, how the height is related to the atmosphere. So think about why we don't have water barometers, and why it is the case that water will not rise up spontaneously without the use of a pump more than a certain amount, that's about 10 meters. So that's it for today.